Hello and welcome to Lab 5. Today our subject is a simulation of the movement of the world's largest rope swing in Utah. The result is that as the rope continues through its swing, the tension of the rope is not greatest at the lowest point of the arc as we expected, but instead elsewhere on the upswing. In order to accomplish that, we have to take a rope with minimal stretch. Coming over to Python. To model the swing, we obtain the initial data given from the behind the scenes video. We start from the gravitational constant, which is 9.8. The mass of the person, which for an average male is 80 kilograms. And from now on, we call him a ball. Then the length of the rope, which was 130 meters. For the spring constant, we put a very high value, close to an ideal spring, and we also set the time initial to 0. Then we created all the necessary objects needed for the visualization. So, let's come down to the loop. We used information to calculate the force of the ball traveling and to calculate the net force on the ball. We used the time 13.70 seconds, which is the time it takes for the ball to make an hemispherical loop, like it would in an actual swing. We then calculated F net and F tangent and F perpendicular. We also calculated theta in order to find the tension force exerting on the rope. We calculated the momentum, and finally we draw the force arrows and printed out the final data from the program. Coming on, we have to run the program. We will see that it is more ideal from the real world because we don't count some other factors that we have in the real world situation, as the air resistance, for example. Let's run the program and see that. The red arrow is the momentum, the cyan arrow is F net, and the white arrow is the gravity force. As you can see right now, the jumper made an hemispherical swing that brought him just above the ground. Just right here. Okay. What I did next is that I separated this swing into 4 equal time parts in order to compare the final tension, the final velocity, and the final position. I ran 4 times the program, and these are my results. As you can see, we have a change in the velocity, and the strange is that the tension of the rope on the lowest point, which means at half time here, is not the greatest as we might have expected. The biggest tension of the rope is found into the swing when the rope is trying to go up and pull the way up against gravity. As you can see, the number 740 and 84 is much lower, much smaller than later in the upswing, here or here. We can tell and we can see the importance of the spring constant if we do this experiment. We go back to our program, okay, and we will change the constant of the rope of the spring and do it smaller, like this, 100. Let's run around the program again to see what happens. See the magic thing that's happening. Okay. This wouldn't be very good for a person in the real world. So we can see the importance of the spring constant. So, conclusions. As we saw, it is very important to choose a rope with a limited amount of stretch. It is fine to have a small amount, but in this case that would be very bad for the person. Finally, the rope must hold a large amount of force without much change in length in order to allow the jumpers to swing safely without getting too close to the ground.